Hello, in this video I'm going to discuss models more, and I'm going to actually talk about the problems that we do in the module in the program. So first I want to remind you what a model is. So a model describes a situation and it interprets vocabulary as talking about that situation. So the universe tells us which things there are in the situation, and that tells us which thing the quantifiers range over, or put slightly differently, what are the possible values of all the variables. And then when we say for all x blah blah blah, or for some y blah blah blah, we're saying for every possible value, for every value of the variable, or for some value of the variable, well, for some value of the variable drawn from the universe. So it's the quantifiers. When we say all objects, it's all objects in the universe. Predicate extensions, they tell us which things in the situation the predicates are true of, and name extensions tell us which things in the situation the names refer to. So in the models, in the Logic 2010, we work in we use models in what's called the invalidity module. So we're using models in a specific way. We use them in the model, in the program. We use models to show that a sentence is not a logical truth by finding a model in which it's false, or we show that an argument is invalid by finding a model in which its premises are true and its conclusion is false. And so it's actually called the invalidity module. So let's go over to the invalidity module and take a look at it. So here we have 3.6 dbk001. So this actually doesn't come out so well on the monochrome version, but this area here is the work area. And you can and so this sort of lets you track what you're doing. You can also do it on a piece of paper if you want. But this doesn't matter to the actual correctness or incorrectness of the problem. What you have to do first, so here we have the universe and the extensions. If we click on this, it says the universe needs to have at least one element. So first thing we need to do is we need to choose how many elements we want. So let's just start with one. And so in a one element universe, we have one element, and that's going to be the number 0. And if we choose, let's say 5, it's going to just be 0, 1, 2, 3, 4, and so on. So we're going to start with a one element universe, because why not? And now what we want to do is we want to show that this is an invalid argument. So we want to come up with, that means we want a model where this is true and where this is false. Okay. So that's fine. Oh, I'm doing too much. I'm doing too much too quickly. Okay, so the first thing we might want to do is think about, okay, well, we need to make this false, and what's the main connector of this? It's the conditional. Well, when is a conditional false? It's true when the antecedent is true and the consequent is false. So we need to make this true and that false. Okay, so how do we make some x fx true? Well, we need there to be at least one thing in the model that makes this true when it's assigned to x. And how does something make this true when it's assigned to x? It's in the extension of f. So, good. So now we've made this true. Now, is this true or is this false? Some x, fx, and gx. Well, what this says is there's something that makes this true. So there's something that when it's assigned to x makes the conjunction true. So there's something that when it's assigned to x makes fx true and makes gx true. Okay, fine, good. So if we assign 0 to x, then fx is true because 0 is in the extension of f. But gx, that's false because 0 is not in the extension of g. So this is true, this is false when we assign 0 to x, and there isn't anything else. So there's nothing that when we assign it to x makes the conjunction true, and so this indeed is false, and so our conclusion should be false. If we check it, well, what it says is this tells us, yes, the conclusion is false, but also the premise is false. And the thing is, we want to show that this argument is invalid, so we need to come up with a situation where we have a true premise and a false conclusion. So the problem right now is that it's good. False conclusion, good, but false premise, bad. We need to make the premise true. Okay, let's look at what the premise says. Well, the premise says if some x fx, then some x gx. If the antecedent was false, then the premise would be true. But some x fx is true because 0 is in the extension of f, and so some x fx is true. And the problem is that some x gx is false. How can we make sum x gx true? Well, one thing we could do is we could put 0 into the extension of g. So now this is true, and this is true. If we do that, though, oh, now we have a problem, because now, well, the premise is now true, which is what we want. The problem is that the conclusion is also true. Why? Well, sum x fx is true, that's fine, but also 0 now is like this. If we assign it to f, when we assign 0 to x, then fx is true, but also when we assign 0 to x, gx is true, because 0 is in the extension of both f and g. So when we assign 0 to x, both of those are true, and so this is true, and so unfortunately, that means the conclusion is true. So what we need to do is we need this to be true, this to be false, and this to be true. And so if this is true, if sum x gx is true, then the premise is true. If sum x fx is true, and sum x fx not gx is false, then the conclusion is false, and that's what we want. So how are we going to make sum x fx true, sum x fx and gx false, but sum x gx true? Well, we have to add another object to the domain. And we need to make it be g, but 0 not be g. So now we have, is sum x fx true? Yes, because there's a thing that's in the extension of f. Is sum x gx true? Yes, because there's a thing that's the extension in g. A different thing, though. Now, is this true or false? Well, if we assign 0 to both f and g, then this is true, but this is false, and so the conjunction is false. When we assign 1 to x, then this is false, and so the conjunction is false. So there's no one object that when we assign it to both f, that when we assign it to x, makes both of the conjuncts true. So it looks like this is true, and this is false, so the conclusion is false because it has a true antecedent and a false consequent. And the premise is true because it has, in particular, a true consequent. So if we check it, it's correct. So this helps us keep track of what writing in here helps us keep track of what truth values we want things to have. The universe and the extensions are actually what do that. So we could delete all that, and it stays the same. I'll do one more problem, and then we'll start another video with some more problems. So let's look at this one. That one? No, we'll do this one. Actually, let's do this one. Actually, this will illustrate my point I want to make. So we have, our premise is it's not the case that for all x fx, and our conclusion is it's not the case that sum x fx. So we want this to be true, and we want this to be false. Okay. Now, negations are hard to read. Oh, actually, so the first thing we want to do is it's easier if we're trying to make everything true, because then we don't have to go back and forth between, am I making this sentence true and that sentence false, or this sentence false? I'm confused. So what we really want to do is we want to make true, and that means we want, oops, wrong place. So what we do is we want the negation of the conclusion to be true. So we have the conclusion, and we want to make the conclusion false. That means we want to make the negation of the conclusion true. Well, in this case, the conclusion is equivalent to that. So that's nice. We can simplify, and so now we say we want to make sum x fx true. And we want to make not for all x fx true. Well, that's actually somewhat easier to understand if we apply qn. Okay? And now it's very clear what we need to do. We need to make this true, and we need to make that true. So we're going to have a universe with two elements. We're going to have, one of them is going to be f, and one of them is not. So this is true, because when we assign 0 to x, this comes out true. So there is an object that when we assign it to x makes this true, and that means this whole thing is true. When we assign 1 to x, then this is false. So this is true. So again, there's a value that when we assign it to x makes this true, and therefore sum x not fx is true. And that's correct. So is something not f? Yes, 1. Is something f? Yes, 0. So true, true. But if this is true, then this is true if and only if that's true. And this is true if and only if that's false. So by making this true, we made this false. And by making this true, we've also made this true, and so we've made this, we made that true, and we made that false, and so our argument demonstrates, and so our model demonstrates the invalidity of this argument. Now what this also demonstrates is two things. First, we want to negate, so instead of making the conclusion false, make the negation of the conclusion true. That's one thing we want to do. The other thing we want to do is we want to sort of confine negations, move them in as far as possible. That makes this this produces easier to read sentences. So it's clear how we do this, okay? Now what about this? Confine or eliminate, as we did in this case, really. Well, we have an answer. We have all these negation theorems, right? So we have both versions of De Morgan's, we have NC, we have NB, and we have both of the QNs. And so what each of these theorems does is it lets us move the negation in while producing a sentence that's equivalent to the original sentence. And that's what we want, because what we're going to do is we're going to make the sentence on the right true, and by doing that we're also making the sentence on the left true. We want to make sure they have the same truth value. So what we do, so these theorems are equivalences, both sides always have the same truth value, and that means you can use them to transform what you're working with in the workspace. So if you have not for all x, fx, and gx, so you can apply qn to get some x not fx and gx, but then also equivalences can be applied internally, not just externally. We haven't talked about how to do that in the derivation module. We probably won't for this course, but know that you can apply them internally. So NC, if we apply NC on the inside, that gives us some x, fx, and not gx, and that it's much easier to think about how am I going to make some x, fx, and not gx true than it is to think about how am I going to make for all x if fx and gx false, or how am I going to make not fx, not for all x, fx, not for all x if fx and gx, how am I going to make that true? So we've seen how to construct sort of what the mechanics are of building a model. First you set the universe, and then you choose the extensions, right? Here you're choosing which things they're on the situation you're talking about, and here you're choosing which things in the situation, if any, the predicate f is true of, and it could be false of all of them, where we've seen predicates with empty extensions. There always have to be things in the universe, but the predicates can be false of everything. And we've seen this idea that, okay, one thing we want to do is make the negation of the conclusion true, and then the other thing is we want to move negations in, and we want to do that using these equivalence theorems. These are the theorems that say when two things are equivalent to each other, but they move negations in, and they make things easier to read, and we can apply these on the insides of formulas, not just to the whole thing. And so when we apply them multiple times, we end up with something easier to read. So that's the end of this discussion of the models. I'm going to do some more invalidity problems and discuss another sort of strategic thing you can do to make it easier in the next video.